Welcome, everyone. My name is Brittany Todd, and I am a member of the Fabric Leadership Team. Thank you all for joining us today for the 7th installment in our Stitching Together Innovation with Fabric Users, led by Ilya Baldin. Next slide, please. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled. If at any point you have a question, please type it into the Q&A box at the bottom of your screen, and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. Next slide, please. We are joined today by our presenter, Ilya Baldin. Dr. Baldin is the Data Fabric Integration Architect for DOE's newest computing facility, High Performance Data Facility, being constructed jointly by Jefferson Lab and LBNL. He is working closely with the ESNet team on the ESNet JLab FPGA Accelerated Transport project, developing the user-facing software for it. He was the PI and project director for Fabric during its construction phase between 2019 and 2023. His research interests include distributed systems, high-performance and optical network architectures, data-centered network architectures, control planes, high-performance data transfer protocols, as well as federated authentication and authorization policies for distributed infrastructure. I will now pass to Ilya to start the presentation.
Thank you, Brittany. It's good to be back in new capacity. Today I will be talking about the project called EJFAT, ESNet JLab FPGA based accelerator transport system. And I want to say I'm representing here a much larger team consisting of engineers and scientists from both ESNet and Jefferson Lab. I'm a relative newcomer to the project. So while you're hearing my voice today, in fact, I'm speaking for a large team. So a little bit of introduction about who the two participating organizations are. They're both part of the Department of Energy. ESNet, of course, is the network that powers the department's research mission. It connects all of its facilities together, as well as connecting them to the outside world, and provides reliable, high-performance connectivity to other global research networks.
Ilya, I'm so sorry to interrupt, but I don't think your camera is on.
Okay, 1 second. Let me do that. How's this?
Perfect. Thank you.
All right. Jefferson Lab is one of the newer laboratories in the DOE complex. It's only, air quotes, about 30 years old. And up until fairly recently, it was a single program, single mission facility that served the nuclear physics research community with its CBAP, a continuous electron beam accelerator facility. However, in recent years, in the past couple of years, Jefferson Lab, together with Lawrence Berkeley Lab 1, the design and implementation award for the HPDF, High Performance Data Facility, which we're jointly working on, as well as Jefferson Lab is now part of the Electron Ion Collider project, jointly with the Brookhaven National Lab. So as a result, JLab now is becoming a multi-mission, multi-facility lab. So let's talk about EJFAT, and it is, even though the acronym is EJFAT, we pronounce it as EJFAT. Why did this project come about? There's a relatively straightforward answer. Today's typical science involves essentially 3 distinct steps. If you have an instrument, and then within the DOE complex, quite frequently it's some type of accelerator that produces particle beams that are then smashed into some types of matter to determine, for instance, the basic properties of matter in the universe. So you run an experiment and you collect the data through something called the DAQ, the data acquisition system, and you put the data in the local storage. Then at some point later, you transfer the data to the HPC resource of your choice, to the storage system of that resource. And then finally, when your turn comes, you run your codes to crunch on the data and kind of discover the things that this data contains. And as you can see, these steps are well defined, they're discrete. And the nice thing about them is that you don't actually have the need to run all the things together at the same time. So in other words, in the first step, you just have the science instrument and local storage working. Then you just need the network and the storage systems. And finally, you just need the local compute and the local storage at the computational facility. But the problem with that approach now is that the scientists are really trying to accelerate the pace of discovery and see whether it's possible to essentially run all of this as a single step. However challenging that might be, it actually opens up new opportunities for kind of closed loop control of the experiment. You might be running, for instance, a digital twin of the experiment in parallel to it and kind of steering the instrument towards the discovery that you're looking for, rather than having to kind of wash, rinse, repeat these steps as shown here on the slide. And so that's where EJFAT kind of comes in. EJFAT attempts to solve the problem of streaming analysis of data, where the data goes straight from the science instrument into a HPC facility or multiple facilities, and then the results are finally stored on the storage system. Of course, you've heard about edge computing, and edge computing next to the instrument can solve some of the problems, but it's often enough not sufficiently powerful. And so as a result, you actually need to borrow computational power from multiple facilities that may be widely geographically distributed. And so that's where EJFAT kind of comes in force, as it were. However, you must notice that this model is fully synchronous, right? All of these things shown on this graphic must be online at the same time. The science instrument, the data acquisition system, the network in between, the HPC system, the storage system, they all must be working in order for this to work. And so EJFAT solves this problem by essentially separating the process of data acquisition and streaming from the process of streaming of processing the stream of data. What it does is it packetizes the event data as it's being sent from the instrument, and then the data in packetized form over ESNet is sent to FPGA-based load balancers. The load balancers then send these little chunks, UDP packet-sized chunks of data towards processing servers, which have previously registered themselves with the load balancer in order to announce their availability. And one of the critical features of EJFAT here is that the reassembly of the events, or the streaming of the events, is coherent. In other words, you can see the different colors here in the diagram showing different events at different timestamps, and then the events of the same color are always sent to the same server. And what that guarantees is that the event can then be reconstructed by a single server in a coherent fashion and then processed. And that is a very important feature from the perspective of data processing pipelines. The other interesting and important feature is the fact that the processing nodes can be completely geographically distributed. They don't need to be part of the same cluster. They can be part of different HPC systems. And the servers don't really need to know anything about the origin of the data. The only thing they know is how to talk to the load balancer. They don't actually know where the data acquisition system sending the data stream sits. And they can come and go, which provides elasticity to the process. So which means that you might have some extra capacity, and if any of those servers, for instance, fail, you can then dynamically replace them with new servers that can continue processing everything in real time, avoiding event loss. I must note that the system is engineered to support essentially terabit scale traffic stream. So far, we've been able to demonstrate live essentially 100 gigabit stream processing, and this year we're planning to scale this up to some significant portion of a terabit per second. This graphic shows just a little bit more detail of how the system works. EJFAT relies on custom headers within UDP packets in order to provide the segmentation and reassembly logic, as well as it adds a gRPC-based control plane so that the processing servers can talk to the load balancer. But again, the important feature here is that the sending side, the DAC, the data acquisition system, only knows a single IP address of the load balancer. And very similarly, the servers processing the data really only know to talk to the load balancer. There's no need for the many-to-many communication here, which simplifies a lot of security arrangements as well as debugging and so on and so forth. We were able to demonstrate the system running, and this presentation and a lot of work shown here is essentially based on the demonstration that we did for the supercomputing conference a couple of months ago. And for that conference, we were able to demonstrate streaming data from Jefferson Lab to the load balancer to 3 computational facilities, NERSC, Perlmutter supercomputer, Oak Ridge, ORNL's ACE testbed, as well as the Fabric testbed and nodes in Fabric, and then also actually send the data back to JLab via the load balancer. An important property, kind of deployment or implementation property of the load balancers, it's in fact virtualizable. A single farm of FPGA, multiple FPGAs under a single control plane can present multiple logical load balancers that can be used independently by different experiments at the same time. And currently, we have load balancers deployed within ESNet that can be used like this. There's a farm of load balancers deployed within ESNet, as well as we have notebooks that allow us to stand up load balancers within Fabric using its FPGAs. This slide shows a little bit more detail about the experiment. The one thing I guess to point out is on the graph on the left, the lower part, you can see different levels of CPU. One is showing, I think, 20,000. The other one's showing 10,000. The key part here is that the load balancer is able to provide just the right amount of loading for each server based on its ability and speed of processing of individual events, so that the servers that are registering or processing the events don't need to have equivalent processing capacity. The load balancer is able to adjust how much work it's offering them on the fly, depending on how much work they're actually doing. And so what you're actually seeing here is 2 types of nodes within the experiment. One very high performance node out of the Perlmutter, and then the second set of nodes is out of the Oak Ridge testbed, as well as from Fabric, which are not quite as powerful as what's available within Perlmutter. The ecosystem for the EJFAT project, of course, is richer than just the load balancer implementation. You have to have a way of balancing or managing your workload, compute resources, as well as segmenting and reassembling the traffic that is being sent. And so for that, there are 2 projects. One's called Giraffe, the resource manager based on a dynamically managed Kubernetes cluster that was developed at Jefferson Lab. And then the other one is called E2SAR, EJFAT Event Segmentation and Reassembly. And that's a client-facing library that provides the logic to segment the events into the right size chunks and then reassemble them once they've arrived into the worker nodes from the load balancer. It's important kind of to mention a few design aspects of EJFAT here. It does rely on low loss ESNet 6 network, where we're able to send essentially hundreds of gigabits per second of UDP packets without ever losing a single packet. So in the current implementation, EJFAT does not provide any capability to deal with the packet loss, although we do have on the roadmap some features, essentially erasure coding, addition of erasure coding to EJFAT to deal with the low amount of losses once we start approaching higher network speeds. As I've mentioned, the event grouping is coherent. That provides the ability for a worker node to deal with the entirety of data for a given event. And then the pool model, which means that the workers, it is the workers who register themselves with the load balancer announcing their availability, not the other way around. That provides a lot of flexibility in terms of how the system can be deployed and scaled. And then the scaling actually is provided in two kind of separate dimensions. One is you can have more than one. In fact, currently you have more than one FPGA, each with 200 gigabits ports under common control plane. So they can be all scaled out under a single IP address to which the data is sent. And then compute nodes can also come and go as needed based on registering or deregistering from the control plane. So E2SAR is the library that myself and my team at JLab have been working on to implement the end-to-end transport for data. It provides currently C++, Python, and we're developing Java bindings for these processes, and it supports multiple E2SAR integration patterns. So to mention a few, the top one is the simplest one. So if you have E2SAR library, you essentially include it into your send side, the data acquisition side, as well as you include it into your receive side, where you're doing the processing. And then it will provide the control plane as well as the data plane features for both of those. We're also have in mind a bump and wire deployment model, where you might have some of your own protocol shown here with blue arrows, communicating from your data acquisition system into this bump and wire implementation that includes the E2SAR, from where the data using E2SAR is sent to the load balance. It's reassembled back in a bump and wire fashion as well, and then sent back to the receiving app. And this is actually a model that's currently being used to implement an interface between E2SAR and an EPIC system within DOE, which is a popular, well-established streaming library. Another approach on which we're considering working on is many of the data acquisition systems are actually FPGA based themselves. So it's not entirely out of the realm of possibility to imagine that a data acquisition system can be constructed in such a way that it directly produces the packets of the right type that can be sent to the load balancer. Of course, on the receive side, it's still mostly software-based, and so you need to use E2SAR to do the processing either directly or through bump and wire type deployment. Some future features that we're thinking of is integrating E2SAR into DPUs that are coming out. Many of them nowadays are actually capable of processing data at line rate, which was not true until fairly recently. But with that, we should be able to implement E2SAR on those. As I mentioned, erasure or network coding and FEC to deal with lossy networks, integration with storage for burst buffer functionality, as well as other widely accepted data streaming systems like EPIC I already mentioned. So in terms of the storage integration, we actually had a poster in supercomputing conference where we demonstrated that using DEOS file system, which is an NVMe-based file system, we can actually sync up to 30 gigabits per second using a single client, which if you think about a stream of 100 gigabits per second, it means we could actually sync only 3 workers using 3 workers, perhaps 4 workers. We could sync an entire stream into a file system if we needed to. The usefulness of a burst buffer kind of comes in multiple dimensions. You can, for instance, run an experiment in the mode where you're just dumping data straight into a data lake, and that's okay. You could, which would be hard without a load balancer, right? Because you actually do need to be able to sync only as much into each client as it is able to accept and not more. You can provide additional resilience by sending data in parallel to the burst buffer as well as into processing, and you can provide elasticity. But the key criteria for a burst buffer mobilization, of course, are high throughput, persistent storage, and diverse storage abstractions, which, by the way, all of these features are supported by the DEOS file system. For those of you who don't know, it was an Intel project, which has now become, I think, a Linux Foundation project. There's a new kind of renewed development effort behind it nowadays. All of this is not in a vacuum. This work is actually we're doing is in the end meant to support HPDF, High Performance Data Facility, that was recently awarded to JLab and LBNL to construct. This is going to be a facility of new kind within the DOE complex, focused purely on data, or more so on data than on compute. And one of the requirements for us with HPDF design is to be able to support streaming science, as opposed to more traditional kind of file-based multi-step transitions. And so in that sense, EJFAT, as it's being developed today in E2SAR, are really intended as starting capabilities for supporting streaming within HPDF. Finally, within DOE, there is IRI activity going on that is intended to unify multiple OSCAR facilities together under common interfaces to support a number of different science patterns, as they're referred to. And one of those well-defined, well-identified science patterns is, in fact, time-sensitive pattern, which, to quote the documents from IRIs, requires real-time end-to-end performance combined with high reliability for timely decision-making, experiment steering, and virtual proximity. And of course, these are all the high notes that EJFAT is also trying to hit. So EJFAT by now has a kind of a well-established place within the IRI initiative. And finally, this final portion of the presentation, we'll talk about how we use EJFAT Fabric to support EJFAT and E2SAR development. It wouldn't come as a big surprise. The surprise that something a test bed like Fabric, or Fabric specifically, is in fact extremely valuable for our development efforts. It provides us the ability to do both testing as well as performance evaluations. It provides sandbox environments where we can do kind of very, very targeted testing and evaluations. We can separate control and data plane testing. We can do the tests using the FPGAs. We can do performance evaluations. We can importantly test IPv6 and IPv4 support. There's a strong mandate within DOE to support IPv6, and so any product or project that uses networks must take this into account, and having a place where this can be tested is very important. We can do various advanced scenario testing. For instance, we can deploy cascaded, geographically dispersed load balancers, and so on. And of course, we can use it for demonstrations, as I mentioned earlier. We've used
advanced scenario testing for cascaded.
We can use it to support and demonstrate how the load balancer it can be used using multiple distinct facilities. And one of the things that we did for supercomputing is actually demonstrate how 3 completely separate, independent facilities with very different APIs and interfaces, like NERSC, Pearl Motor Supercomputer, the Oak Ridge ACE testbed, and Fabric, can be used together within a single workflow. And that's what we were able to demonstrate using the elements that I talked about. Just to say a few things about how we're using Fabric. We have multiple notebooks within for instance, the E2SAR development team that we're using for different purposes to test or benchmark different portions of the system. So one of the simplest tests, or one of the simplest slices we have, is what's shown here. We just have a simple layer 2 network connecting 3 nodes. One of them runs a control plane with no FPGA. It's a kind of a null FPGA where but the control plane API themselves can be easily tested. And then we have sender and receiver, so we can actually, even without a load balancer, we can test a single sender against single receiver. And of course, it's a scenario that must work, and in fact is interesting to benchmark as a foundation for other benchmarks that involve multiple senders and multiple receivers. Another example, actually, let me go forward here. Another example is the demonstrations that we did for supercomputing or other events. And sort of in the top right of this diagram, you see the schematic of what was actually being shown. You have data being streamed from JLab over ESNet6 to load balancer, which then distributes the traffic to three different facilities, Oak Ridge, NERSC, and Fabric. And then the results are actually sent through another virtual load balancer back to Jefferson Lab for processing and storage. And what is of interest here, of course, is the Fabric slice. So what's shown here is a result of a notebook that can actually build a slice out of multiple very large virtual machines, 64 cores. For Fabric, that is the limit. And it uses the modify feature of the slice kind of management, where the slice is built a little bit at a time, such that if any allocation on any given site of a given virtual machine fails, it just moves on to another site where more capacity may be available until it essentially builds the requisite number of virtual machines, which can then be loaded with the processing software on which then register themselves with a load balancer, and the experiment then commences. And probably the most sophisticated for now, at least, the use of Fabric is this three separate slice diagram, where we build an actual load balancer using the FPGAs within Fabric, and we actually use a storage slice for that, which is where we store the Docker images needed to stand up the control plane as well as the data plane on the load balancer. And the reason why we use the storage slice is because the FPGA firmware is not open, and we don't want it posted publicly anywhere. And then we can separately stand up one or more worker slices that have one or more senders and some number of receivers or worker nodes. And then once the FPGA slice is up, the senders can start sending data, and then the receivers can start processing it. We have within the E2SAR library, we have an application called E2SAR Perf, which is loosely based on iPerf, but with specifics kind of tied to what E2SAR actually, or what EJFAT actually does. And so we use that application to benchmark and test the performance of the application under different scenarios with different numbers of workers, different numbers of senders, and so on and so forth. So that's probably the most sophisticated way in which we're using Fabric. I should mention that within this slice, we use FabNet v4, the internally routed v4 network. Then with the other slice, we're actually using FabNet v4 ext, which is the one which is uses the peering locations that Fabric has with production networks, including ESNet, and allows us to send traffic outside of Fabric and then receive traffic from outside of Fabric in this scenario. Again, the amazing thing here is that in all the testing, we have not seen packets being dropped neither by ESNet nor by Fabric, at even sending it at high rates, where the total rate shown in the slide is 100 gigabits per second being sent towards the load balancer. I think that concludes the majority of my presentation. If you're interested in learning more about our project, we have a little QR code. You can contact us. As I said, it is a large team working on this, both developing the FPGA firmware and the control software, the client software, and so on and so forth. And to acknowledge the funders, this was funded by a number of programs and projects. And at this point, I will open to questions.
Yes, thank you so much, Ilya. I appreciate it. As Ilya said, now we'll move to the Q&A session. So we'll begin with the questions that were submitted during the presentation, and we can stop screen sharing to begin addressing these questions. So the first question that we have is, what did you consider in choosing an FPGA-based data plane versus a programmable switch or GPU-based solution? Are there scenarios where a programmable ASIC like a Barefoot Tofino might be preferable?
I think the consideration here, and it predates my participation in the project, the FPGAs were selected as basically the most programmable and as well as cost effective. I saw another question. So the team working on this is from ESNet side is the same one that developed the P4 workflow that is used in Fabric. And so that's the workflow we use. And the actual firmware running inside the FPGAs is in fact a P4 program that does the load balancing. So I think that the FPGAs were chosen as basically the most programmable and most cost effective. As you all know, with Tofino, there's a lot of uncertainty now whether, you know, how the development will proceed with different types of switches. And in terms of ASICs, again, we are still developing the protocol, and so you know, spinning an ASIC is an expensive and fairly time-consuming and you know, costly proposition. Whereas with the FPGAs, we can in a fairly agile fashion change the details of the protocol in order to support the development for our current and potential customers within the DOE complex.
Thank you. The second question is the scale of what you are currently working on able to be replicated?
I think if I'm reading the question, so this is fully replicable in the sense that we are able to run these workflows at 100 gigabits per second multiple times. This is not a one-off. And as I said, our next steps actually are to scale up to multiples of hundreds of gigabits per second, somewhere towards a terabit. You know, how far we get, we shall see. But it's certainly something that we can repeat in a fairly regular fashion.
Thank you. Next question. Are you using the ESNet SmartNIC stack or are you flashing the FPGA?
It's yes and yes, I think is the short answer. The workflow that's used to flash the FPGA to support load balancer is very similar to the P4 workflow used in Fabric. So we flash the FPGA with the firmware that we have.
That's great. Next question. You use unique features. Are there some hurdles you need to go through to obtain those levels of performance?
In terms of, yes, so we are using some unique features of Fabric. For instance, its ability to peer with production networks is extremely valuable in this context to us, as well as the ability to stand up FPGA-based load balancers programmatically. Essentially, you know, we have a number of notebooks that just stand up each and every piece that I showed you, and they're all pretty reproducible, which makes us extremely happy, because that means we can focus on the work that we're doing, the value add that we're doing, rather than debugging things. So essentially, every new attempt to get to higher speed, of course, involves a lot of debugging and work on our part to trying to figure out if we're seeing, you know, artifacts of behavior from our own code or from something else. But in general, it's been a really positive experience for us integrating Fabric. It only took us about 4 months maybe to integrate Fabric into the workflow. So that's, you know, and that's not full time, right? That was just on and off us working to get that to happen.
Wow, that's really impressive, actually. Next question. For your experiment, do you normally need to run over a long time or short bursts?
The answer is relatively short bursts that last a few hours, for the moment at least. Some of it is governed by the allocations that we're able to get at, for instance, NERSC. So while Fabric is kind of on demand and best effort, but we can get the capacity we're looking for generally. At NERSC, our allocations start at specific time and end at specific time. So we have to be cognizant of that.
Thank you. And last question, unless another one comes in. You mentioned FabNet V4 I think EXT. Do you have security concerns with it being connected to the public internet?
Yes, we're using that type of fabric network, which essentially allows us to connect virtual machines to the public internet, in this case IPv4. And yes, of course, there are security concerns. Our notebook that we built, actually with some consultation with the fabric team, goes to great lengths to limit the possibility of it being abused by someone from the outside world. So we only open the routing as well as the firewall towards known IP address destinations that we have, as well as to only open known ports and so on and so forth. So there's a number of steps we take in order to make sure that essentially the computational resources inside those slices aren't abused.
Excellent, thank you. And I don't see any other questions coming in. So I want to just give one more thank you again to our presenter, Ilya Baldin. In addition to our presenter, we would like to acknowledge the behind the scenes team listed coming up here on your screen, who worked diligently to bring this webinar to production. Next slide, please. And thank you also to the audience for your participation in today's webinar. In addition to a recording of this webinar, we will also email everyone who has registered a list of resources. This slide deck will be shared along with our Connect with Us form. We hope that you will reach out to the Fabric team for any questions you have or support you may need. Our next webinar is next month. It's Mastering Fabric Tips and Tricks webinar, and it will be on February 18th at 3 p.m. Eastern. This webinar will be focused towards existing users and will focus on the topic of route networks with performance enhancements via hardware offload. We would appreciate it if you could forward the information to the relevant users in your communities. As a final reminder, please submit your Fabric matrix and make sure your project description in the portal is up to date, as we will use that information for outreach, including our website. Thank you again and have a wonderful day, everyone.